So question number 1. What is the pH of a buffer solution prepared by mixing 25 mils of 0.10 moles per litre ethanoic acid and 25 mils of 0.10 moles per litre sodium ethanoate? And then you're told that the pKa of ethanoic acid is 4.76. Just to try and catch you for a start, the question includes this thing here. So this is the sodium salt of the conjugate base, right? This is like sodium chloride or sodium hydroxide. This is sodium ethanoate. If you wanted to make up this buffer solution by taking chemicals off the shelf in the lab, then you can't go and get a bottle of ethanoate ions, right? They don't exist by themselves. It will be present as a compound, as an ionic compound, where ethanoate is the anion, and in this case, sodium is the cation. And we're normally going to give you either sodium ethanoate or, no, actually, it'll just be sodium ethanoate. Does anyone want to suggest why it's always going to be sodium ethanoate? Because it's... Someone said a word over here somewhere. Sorry? It's easy to dissolve. Why is it easy to dissolve? It doesn't affect the pH, that's true. The sodium won't affect the pH, it is a spectator ion. But in your lab in last Wednesday, I suppose, you in your lab manual had something called a table of solubilities, yes? And what was rule number 2? All sodium compounds are soluble in water completely. See, those solubility rules are actually quite useful just beyond that lab, especially in all this acid-base chemistry, because what we'll do is we'll always use sodium compounds, right? You could use lithium ethanoate, undoubtedly you can get that in a bottle, or calcium ethanoate, but there's no guarantee that those are going to be completely soluble in water, and then it just confuses everything. It would make for an interesting question, actually. You could build you could do a KSB calculation to work out the concentration, and then use that concentration in working out your buffer. But we don't tend to do that. We probably should, but we don't. So we're going to use sodium compounds all the time, because then you can just say, well, as soon as I see sodium ethanoate, then the concentration of that will be the same as the concentration of ethanoate ions, because that compound will completely dissolve in water to give sodium cations and the anion. Yeah, you see what I'm saying? So it's one of those things that if you forget to notice, it probably doesn't matter. But that's why it's always going to be sodium. Okay, so the first thing to do is to calculate the amounts of the acid and the conjugate base.
Do we not just go by the concentration?
No. Why? Anyone? Why would we not just use those concentrations? Because they'll be wrong, right? Because when you mix those solutions together, those concentrations will change.
Will they just halve?
Well, they will just halve, but you have to be onto it to do that. And what I'm saying is if you work out the amounts over all of these different problems, this is going to be, in general, an easier way to go, right? We're talking about the ratio of the concentrations, so even then it's not going to matter. But if you do your nice working, and you write in the concentrations and the concentrations are wrong, then the marker goes, oh, see, they weren't thinking about that, half a mark off. Whereas if you just work out the amounts every time, then you'll be sweet, right? So let's work out the amounts. The amount of the ethanoic acid is equal to the concentration times the volume. So it's 0.1 moles per litre, the concentration, times 0.025 litres, which is the volume, but in litres the way it has to be. And so that comes out as being 2.5 times 10 to the negative 3 moles. And if we do the same sort of calculation for the ethanoate, then we get the same answer, because the volume is the same and the concentration is the same. They won't always be. I've done this deliberately in this first case. It's deliberately straightforward to make a point. But these concentrations and volumes will normally be all different to each other, right? Okay, so if we've got those two amounts, we've got that? Then we can just write out our Henderson-Hasselbalch equation, and we write it in the form where we have amounts, because that's what we've worked out now. You could convert those back to concentrations if you wanted, but then that's another two calculations, right? You can just stay with the amounts and you'll be fine. So the pH is equal to the pKa, which you were given in the question, 4.76, plus the log of the amount of conjugate base over the amount of acid. And so that's going to look like this for this particular problem. The pH will be equal to 4.76 plus the log of 2.5 times 10 to the negative 3 divided by 2.5 times 10 to the negative 3, because those concentrations are the same. And then what you find is that because those two amounts are the same, the ratio of them is equal to 1, right? Any number divided by itself will be 1, and the log of 1 is 0. And so this whole bit on the end just disappears, and we can say that the pH is just the same as the pKa, 4.76. And so that's an important enough result that I've written this slide with big letters. When the amounts of the acid and the conjugate base are the same, the pH of the buffer solution is the same as the pKa of the weak acid. Right? So that will always be the case. If you have those concentrations or those amounts of the two components of your buffer being the same, then the pH of the buffer solution is equal to the pKa of the weak acid. Okay, so that's, I suppose, the easiest way of us asking you a buffer question. We give you volumes and concentrations of the two solutions which you mix together to make the buffer, and then work out the pH from there. Okay, question number 2. At a certain point in a titration between a weak acid and a strong base, 10 mils of 0.100 moles per litre sodium hydroxide solution has been, so that's in the burette, yeah, has been added to 20 mils of 0.100 moles per litre ethanoic acid solution, which is in the little flask. Calculate the pH at this point. Okay, so now this is different, yeah? Instead of mixing a solution of a weak acid with a solution of its conjugate base, so the two components of our buffer solution, now we're mixing weak acid with strong base. Right? So you can't just work out somehow the concentration of hydroxide and put that in on the top line of your Henderson-Hasselbalch equation, because that equation is about the concentration or the amount of the weak base, the conjugate base, not hydroxide ions. So we have to work out now what these amounts are as a result of the reaction which is going to happen when we mix these two things together. Yeah? And so what I'm going to propose, and we're going to see this over the next few little questions, is that we work through this using a wee table. And the first thing to do when we're setting up our little table is to calculate the amounts of the acid and the strong base, in this case, in question, before the reaction takes place. Right? So we imagine that we've got our weak acid in a container here, and we've got the amount of strong base we're talking about in another container here, and we're going to calculate the amounts of each of these in these beakers before we mix them. Right? So the amount of the acetic acid initially, see little I's here again for initially, equals concentration times volume. And you're given the concentration and you're given the volume in the question, so you can work out the amount. It's going to be 2 times 10 to the minus 3 moles. And then we do the same with the hydroxide. And then here comes our wee table. Now we consider the reaction that is occurring when we add the base to the acid. And so here's the reaction that happens. The ethanoic acid reacts with the base. So when you add the hydroxide ions, they react with the ethanoic acid to make ethanoate and water. Oh look, we're really dragging this out. And note that the mole ratio is 1 to 1 to 1 to 1. Like we said yesterday, it's pretty much always going to be the case for these acid-base questions. We could make them harder, but then they're only harder than this because of math, not because of chemistry. So why bother, really? So one ethanoic acid reacts with one hydroxide to give one ethanoate and one water. Okay, so what I'm going to suggest then is that you write out the equation again, but you write it out with a gap on the left-hand side of your piece of paper, because we're going to write some stuff there as well. So if you write out this equation like this, for probably the 6th time today already, and then what we're going to do is over here, we write before reaction, and then underneath each of the species in our chemical equation, we're going to write what those amounts are before the reaction occurs. So when we've still got the hydroxide in one beaker, and we've got the ethanoic acid in the other beaker, right? And so those amounts are what we've just worked out. The amount of ethanoic acid is 2 times 10 to the minus 3 moles. And the amount of hydroxide ions is 1 times 10 to the minus 3 moles. Okay, and you could argue that at this point there will be a small amount of ethanoate ions present because the ethanoic acid will be reacting with the water a little bit, but the amount is going to be so small compared to these numbers that we don't have to worry about it. Yeah? So we can consider that the amount of ethanoate is 0. It's actually going to be something like 1 times 10 to the minus 7. But like I say, very small number compared to the numbers we're talking about here. Okay? So this is initially, and then of course what we do is we imagine mixing the two solutions together. And now we want to think about how these amounts of the different things change when the reaction happens. So first of all, let's think about the hydroxide. When the reaction's finished, what amount of OH minus will be present? Be bold.
0 moles.
0 moles, right? Because it fully reacts, and it's the limiting reactant in this reaction, yeah? Because of the 1 to 1 to 1 to 1 mole ratio, you need the same amount of ethanoic acid as there is hydroxide for complete reaction, and there's less hydroxide than there is ethanoic acid. So the reaction will happen until the hydroxide runs out, and then it will stop. And so at that point, there's going to be no hydroxide left, right? So we can write a 0 there. And now, what will be the amount of ethanoic acid? The amount of this stuff that will be left after the reaction will be the amount that you started with minus the amount that reacted. And so you're going to be left with 1 times 10 to the minus 3 moles. And then, what about the amount of ethanoate? What will that be after the reaction's finished? Because it's a 1 to 1 to 1 to 1 ratio, if 1 times 10 to the minus 3 moles of hydroxide reacts, that must make 1 times 10 to the minus 3 moles of ethanoate, right? Because the ratio here is 1 to 1. If that amount of hydroxide reacts, it must make that same amount of ethanoate. That's what the balancing tells you, yeah? And so that amount will be 1 times 10 to the minus 3. So this one is this number because that's how much is left over after this amount of this has reacted with this amount of this, and this is the amount that's produced. Now these numbers probably could be better in that they could be all different to each other. But then again, I'm still trying to make a point here. In the next question, I think the numbers are all different, so maybe that'll be maybe less confusing. But does this kind of make sense what we're doing here? Right? And you see how if we set it out in a table, then it makes it nice and clear what's going on, before and after. Yeah? So then, now what we've done is we've worked out the amounts of our weak acid and its conjugate base after the reaction has finished. And these are the numbers that we need for our Henderson-Hasselbalch equation. Right? So it's not these ones, not the 2 and the 1, but the 1 and the 1. Yeah? And so now we can put them back in. And what we find is what we found before. Because in this particular situation, the amount of the conjugate base is the same as the amount of the weak acid, then the pH of your buffer solution is equal to the pKa of the weak acid. So again, it's equal to 4.76.
Is the pH always going to be around about that, like 4.5?
Why? No, you're right, but why do you say that?
Because that's what it looks like on the graph.
Where it's flat.
Yeah.
Good man, yeah, that's exactly right.
So if
We-
you get something that's not around there, then you know you did it wrong.
Yes. Yes, if you do the math and you come up with 1.76, you've done it wrong. That's good, actually. That's because a lot of what we do in the mid-semester exam, where it's all multi-choice, is we can ask you questions about buffers, and in theory, you can then sit down and spend 5 minutes doing some great convoluted calculation or a whole series of calculations to see which of the 4 answers we give you is right. But if you take a step back and you go, well, which of these answers seems right, based on what I know about buffers, you can save yourself a lot of time. And that's exactly one of the things that you should look for, is that if we give you the pKa, and then one of the pHs that we propose that the buffer solution has is miles different to that, then that will always be wrong. Because the pH of the buffer solution must always be quite close to the pKa of the weak acid. And if you think about that flat region in the titration curve, that gives you that sort of tells you how that works. Sir?
So if you're say when you're strong acid weak base, buffer might be 1 minus.
Yes. Yes, because the pKb for ammonia is 4.76, so the pKa for ammonium is about 12, 11, so yeah, about there. Yeah. Yeah. In theory, there's another version of this equation you can use that has a pKb in it, but we never do that. Right? So don't worry, you will never have to do one with a pKb, because then people are never sure whether you flip the concentrations around. And to be honest, I'm not sure either. But we never do that form of it, so don't worry about it. Yeah? So now what we've shown then is that if we add 10 mils of hydroxide to 20 mils of our ethanoic acid solution in our titration, then we get to a point where the pH is equal to the pKa of the weak acid, and of course that's what you saw yesterday. This is the point halfway to the equivalence point in your titration, and we asked you about this in the lab yesterday. You said estimate the pKa of the weak acid, and the way that you do that is by looking at your complete titration curve, looking at what volume of base you had to add to get to the equivalence point, and then halving that volume back to here to point C, and saying that at point C, what I've got in my solution is exactly the same amounts of my weak acid and my conjugate base. I've added half the amount of hydroxide I need to turn all of my weak acid into conjugate base. And so at that point, I must have half of the weak acid turned into conjugate base and the other half still there. So the amounts are the same. And what the question we've just gone through with the Henderson-Hasselbalch equation shows you is that if those amounts are the same, then the pH of your buffer solution is equal to the pKa of the weak acid that you're using. And so if we give you a curve like this, then you can estimate the pKa by just looking at what the pH is at the point halfway to the equivalence point in your titration. Yeah? And of course, I should point out that this curve obviously is not a curve for for ethanoic acid, because the pH here is the pH here is 3.6, right? So it's for a different acid, but the idea still applies. Okay, and so the last slide before a break says that, as I've said lots of times now, if we give you a problem that involves a weak acid, then we will give you the pKa or the Ka. The only time where that will not be true is if we give you in the question the titration curve for the weak acid being titrated with hydroxide ions, and then we can get you to estimate the pKa from that titration curve, right? And then you might then use that number in your subsequent calculations. So if we don't give you the pKa or the Ka, then we will give you a titration curve and you can work it out from that, so long as you know this thing that we've just been talking about. Yeah?